Hello, good morning. Welcome to lecture week 9. Quite fast. We have reached to week 9. Well, we are looking at in week 9, we are going to explore the second option pricing model. Last week, we studied the binomial model, which was a discrete model where from a certain time at the beginning to the expiration time, there's only two outcomes. It is quite a straightforward model and quite versatile. But however, today we're going to explore the Black-Scholes model. Some books refer it as Black-Scholes-Merton model, and lately the Merton has been uh, not there. We call it as Black-Scholes model. One basic important thing about Black-Scholes model is a continuous compounding model. So it captures almost all the movements, the sensitivities of the underlying asset. Mainly, we use the stocks. Okay, let us go into the lecture now. The unit lecture outline will be first we introduce a brief introduction where we'll talk about a comparison between the binomial model and the Black-Scholes model. Then the very important part is the Black-Scholes assumption and formula itself. There are some assumptions which are underpinning this Black-Scholes model, which is essential to estimate the Black-Scholes call price and the put price. Then I'll give you a numerical example where you can appreciate the very celebrated equation, the Black-Scholes model equation, how to calculate that. The basic thing is you have to identify the D1, D2 and convert it into ND1, the normalized table, ND1 and ND2, and apply into the equation to identify what is the call price or the put price. Okay, then we will see the derivation approach, which is optional. We may go deeper or may not. And then we will follow up with interpreting the Black-Scholes model. Formula looks so complicated and complex, but interpreting it is very easy, very simple. Then we will move into working with the Black-Scholes historical versus implied volatility. The volatility part of it, generally or largely we use historical volatility, but there is also a way of using implied volatility. The very difference is that historical volatility uses the stock price to calculate the returns, the standard deviation of the returns regressively for past 1 year. So we calculate the annualized return variation. While implied volatility is where we use the current option value itself, option price. So therefore, these two volatilities can be compared, but we'll see which one is more versatile. Finally, okay, all this while we have been doing on derivatives or what we call options which did not have stocks, which did not have any dividend pay. But finally, we'll touch into how dividends affect option pricing. What happens if there's a dividend? Okay. Now, objectives. This lecture presents the Black-Scholes model or BS model. It describes the assumption of the model and to provide an intuitive understanding of the structure of the Black-Scholes option pricing formula by relating the formula to replication and risk neutral pricing. Well, I'm a bit struggling to lecture this because this is the fifth time I'm recording. I'm sorry, the technical issues. First time we did not record properly. The second time it was not smooth. Third time it did not capture at all. Fourth time it captured, but there's no sound. So hopefully this time it works. Well, this lecture presents Black-Scholes model. It describes the assumption in the model to but provide an intuitive understanding of the structure of the Black-Scholes option pricing model itself, relating to the formula, to the replication, and risk neutral pricing. Is both replication of the underlying asset with some cash and the risk neutral probability that it will be exercised. So introduce to the notion of implied volatility as I told you just now, and discuss the possible sources of implied volatility, the skewness of it, and to relate these to shortcomings in the Black-Scholes assumptions. Okay, option pricing. As I told you, it is very much on replication. Basically, when you see a replica, what's meant by replication? We design a model by not really going into it, but we see how it works. Option pricing follows the same lines as the forward pricing, where is it overvalued or undervalued. So we want to see whether the option price is the rightful price. The basic idea is replication. We look into creating identical payoffs to the option using what long short position in the underlying, usually stock prices, and cash, default free investment and borrowing. That's why we use the risk free rate. Once we have a portfolio that replicates the option, the cost of the option must be equal to the cost of replicating it. Okay. Once you know the replication will provide you what kind of a cost that will be used as a replication or used as the reference to the option price itself. Thus, the challenge in identifying the composition of the replicating portfolio. Well, don't worry about all these big jargon words. We look into the real idea. But an added complication is that volatility. Volatility is the only variable in the option Black-Scholes model which is not directly observable. So therefore, we have to estimate it, without which we can't figure out the BS model itself to calculate the option price. More generally, we need to model uncertainty in the evolution of the price of the underlying security. How much of uncertainty here? We are looking at the risk factor where it is the standard deviation finally which is going to denote all these things, and we signify it with a small sigma. This introduction model dependence, this introduced model dependence. What is it largely dependent to? Option prices are only going to be as reliable as model used in obtaining them. Otherwise, the central issue here is the uncertainty. The volatility is going to determine the option price more. Is so much dependent. Without the volatility component, you can't estimate the option price here. It is in this dimension that distinguishes the different option pricing models. They differ not only on how the price options, how they price options, but also on how they model the evolution of the uncertainty. How do you capture the uncertainty? If you can capture the uncertainty correctly, that means your option price is correct. Key option pricing models. Well, let us see. There are only two. There are two widely used classes of models here. Last week you studied binomial model, which is a discrete model. And now you are looking into Black-Scholes model. What is so great about Black-Scholes model? Black-Scholes model offers closed form solutions for option prices. It is more inclusive. It is very much inclusive on all the sensitivities. Thus makes computing option sensitivities very easy. This feature is very useful for option price hedging, but is more technically complex than the binomial. Binomial, you had only two outcomes, either up or down, and when you estimate the probabilities of ups and probability of downs to the ending nodes, then you can work back by discounting them. But here, no, you have to follow through an equation. You have the normality table also, but still it's not very complex as I see it. It's relatively limited, no closed forms of early exercise. Therefore, we are not going to consider American options at all here. American options cannot be estimated here because the historical, the strike price may not have a proper time value. Because anytime you can exercise it. Early exercise is possible in American option. So we do not consider American options in Black-Scholes model. The binomial model is more flexible and intuitive. Why? Because it is most commonly used form. It can approximate the Black and Scholes framework arbitrarily closely. It's somewhere there, but sometimes it may not. but it can also do much more. Black binomial model can do even much more because it can be used also for American options. One shortcoming is no closed form solutions for binomial. But that part we are capturing it in Black-Scholes. Why? Because in binomial model, it's a jump. It is as though the price existed today of the underlying asset and the price exists after 2 months. In between, what happened, we don't know. It's not a continuous capture. It is a jump. There's a huge gap. What happens in between, we don't know. So therefore, there's no issue about volatility there. There's not much of volatility involved. In this lecture, we focus on Black-Scholes model for pricing options. Let us see. Black-Scholes models is unambiguously the best known model for option pricing right now. Okay? It is quite thorough, quite intuitively capturing all the possible movements of the underlying. It is also one of the most widely used. It is the benchmark for modeling the option pricing option for equities, for stock indices, for currencies. Currencies specifically, there's a black model which is we are not including in this syllabus. The black model is also commonly used for some interest rate derivatives such as caps and floors. However, don't worry too much about that now. Okay, the preliminary comment. Let us look at the preliminary comment first. Technically, the Black-Scholes model is more complex than the binomial model or other latest models. Black-Scholes model that's why I told you Black-Scholes model is a continuous time model. It captures every movement of the stock price. Price in the model are allowed to change continuously rather than at two discrete points like what the binomial is. Binomial just say now and then, that's it. All returns, interest rates, etc. are quoted in continuously compounded terms. Modeling the continuous evaluation of uncertainty requires the use of some sophisticated mathematical including techniques drawn from the field of stochastic calculus. But don't worry about stochastic calculus here. We will very simplify it only by one normality table. In this lecture, I do not delve much into the mathematics aspect of it, instead focus on the intuition of it and your understanding of what you mean by Black-Scholes method model in option pricing.